Okay, Module 9 is about the second law of thermodynamics. We will cover Carnot cycle for this module. Okay, we have the same course outcome. By the end of this module, students should be able to explain, to describe the Carnot cycle and examine the Carnot principles, the idealized Carnot heat engines, refrigerators, and heat pumps, to determine the expressions for the thermal efficiencies and coefficient of performance for reversible heat engines, heat pumps, and refrigerators in terms of Carnot cycle, and solve problems related to heat engines, heat pumps, and refrigerators for both reversible and irreversible processes. Okay. So the contents, this time we will cover the reversible and irreversible processes. You will be introduced what is the Carnot cycle, thermodynamic temperature scale, and the heat engines, refrigerators, and heat pumps for the Carnot cycle. Okay, reversible process is a process that can be reversed without leaving any trace on the surroundings, and the irreversible process is a process that is not reversible. Okay, so example, reversible, A producing B and B can be producing A again. But for the irreversible process, when A producing B, B cannot be processed into A again. Okay, so that just a simple way to understand the processes. So all the processes occurring in nature are irreversible. So why are we interested in irreversible processes? Because they are easy to analyze. Okay, so it is easier for us to identify something and to calculate. Okay, and they serve as idealized models, which has theoretical limits to which actual processes can be compared. Okay, so it's easier for us to identify, to study what is going on, okay, in certain processes. Example, we have frictionless pendulum. This is reversible processes. Okay, quasi-equilibrium expansion and compression of a gas. So you can compress, you can expand. Okay, for this one, slow reversible processes. Expansion for pressure distribution. Okay, so this is the water. Okay, and this is the example of compression. Okay, it's just the same. Okay, and the fast irreversible process, what happened when you push it quick, very quick, and so this is what happened to the bulk of the fluid, the flow of the fluid. Okay, and this is the fast processes for the compression. Okay, so the factors that cause a process to be irreversible are called irreversibilities. So they include friction, unrestrained expansion, okay, electric resistance, deformation, and chemical reactions, and the others. So the presence of any of these effects renders a process irreversible, such as friction. Okay, we have frictions in here. Okay, so these can cause irreversibilities. So an irreversible heat transfer process, okay, higher to lower temperature. So this is irreversible heat transfer process. So and this is an impossible heat transfer process. It is from lower to higher temperature. So this is impossible. And also unstrained expansion. So this is fast compression. What happened to the fast compression? So it's still okay. But for the fast expansion, what happened to the fluid motion, fluid movement in the piston? So this is unrestrained expansion. Again, unrestrained expansion. So internally and externally reversible processes. By internally, if no irreversibilities occur within the boundaries of the system during the processes. Okay, so externally reversible, if no irreversibility occur outside the system boundaries. So for totally reversible process, it involves no irreversibilities within the system or its surroundings and can be restored to their original conditions. Okay, so a totally reversible process involves no heat transfer through a finite temperature difference, no non-quasi-equilibrium changes, and no friction or other dissipative effects. Okay, so this is totally reversible, and the thermal energy reservoir at 20 to 1 degree Celsius. Okay, so this is totally reversible. But for this one, thermal energy, this is too high, too lower. So this is totally reversible. For this one, internally reversible, thermal energy reservoir at 330 degrees Celsius, and this inside we have 20 degrees Celsius. So this is internally reversible, right? Internally reversible.